8.4 we're graphing rational functions. In 8.3 we graphed just reciprocal functions. But a lot of what we did in 8.3 will apply to 8.4. However, instead of the numerator being 1 or a constant, okay, the numerator is now going to be another polynomial, okay? And when the numerator is not just a constant, when it's a polynomial, the rules change a little bit. But some of the things that we've already learned in 8.3 will apply here in 8.4. Everything about asymptotes, everything about undefined values, everything about graphs, everything about your calculator being able to use your table from your calculator, all that stuff is still going to apply. But this first slide is all going to be some new rules because of the fact that the numerator is no longer just going to be a constant. Okay? So, let's start there. And this key concept box, I'm going to show you part of it at a time. So if you want to take a picture of it, wait. If you want to take a picture from your book, obviously you will have the entire box, and this box comes all the way down to here. And I'm just going to show you, reveal part of it at a time, just because there's a lot to take in. All right. So here's the key thing. Okay. We're talking about this function f of x, or g of x, or h of x, or whatever it's called. Okay. And the numerator is now a polynomial, and the denominator is also a polynomial. So a of x represents a polynomial, b of x represents a polynomial. The reason it says no common factors, we're making sure that our polynomials on top and bottom have already been reduced when possible. We factor them out, cancel common factors if possible, that the state that it's in its simplest form as it is. Okay, so there's no longer any common factors. We've eliminated them, and of course b of x cannot equal 0 because that would make this function undefined. Whenever a denominator equals 0, it is undefined. So that's the key thing here, okay? A of x over b of x has already been reduced. The common factors have already been canceled out. And this b of x, the denominator, cannot be equal to 0. Okay, so that's the first thing. Depending on what a of x and b of x are, dictates what our next moves are. Okay, so there's a bunch of conditions that come next. Those of you who've already looked it up in the book, you can see what some of those conditions are, but I'm going to show them to you one at a time. First thing, f of x has a vertical asymptote, okay, whenever b of x equals 0. Again, what this means is whatever it takes to make this undefined, whatever value for x that you plug into this bottom to make it equal to 0, creates a situation where the whole fraction is undefined. Therefore, whatever values make b of x equal to 0 means that there are vertical asymptotes there. And on your quiz, there was, on the back, there were two questions that, there's one question that had two vertical asymptotes because there were two values for x that made the denominator equal to 0. Okay? So that's the key thing. Vertical asymptotes are related to x. What values for x will make the denominator equal to 0. So that's the first thing. So that's how you can find your vertical asymptotes. Next part. Here's where we get some of these conditions. Oh wait. F of x has at most one horizontal asymptote. And sometimes it will have none. Now, one of the things that we looked at when we looked at reciprocal functions was that number sort of added or subtracted outside of the fraction was where the horizontal asymptote occurred. That is not how we look at it for rational functions, and I'll show you all of that here in a second. Okay, at most one, so there's never going to be more than one. In some cases, there might not be one at all. Okay, so here's all the different conditions, and these are things you're going to need to know moving forward, particularly for your homework, and obviously for your test in another week and a half or whenever it is. Okay, so if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. And remember when we talked about degree back in chapter 5, I think, right? Degree is the highest power on the variable. So if the numerator's degree is bigger than the denominator's degree, no horizontal asymptote. And we're going to look at some examples here in a second. That's the first part. Next part. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is f of x or y equals 0. Okay, so this is a lot like what we looked at with reciprocal functions, because the reciprocal function, the numerator had no variables at all, so the degree was 0. The denominator was a linear function, so the degree was 1. And most of the time, the horizontal asymptote was f of x or y equals 0 unless there was a number added or subtracted to the outside of the fraction. So this one is more in line with what we did in 8.3. So, of course, we have the situation where the numerator is greater than the denominator, the degree. The numerator is less than the degree of the denominator. And then, of course, what one is left? Equal to. Now, here's where it gets very different from what we did in 8.3. If the degree of the numerator and the degree of the denominator are equal, then the asymptote is actually a line completely different from this. And what you end up doing is you divide the leading coefficient of the numerator. The leading coefficient is the coefficient that goes with the highest degree. And then divide that by the leading coefficient of the coefficient that goes with the highest degree on the bottom. And then you have this constant, whatever it's going to be, y equals that line, that number, and then you'll get a horizontal line that way. So when you're working on your homework and you're trying to decide about the horizontal asymptotes, because let's face it, the vertical asymptotes are easy. You set the bottom equal to 0, solve for it, and then you know your vertical asymptotes. The horizontal asymptotes, you have to decide which of these three cases am I looking at, and then you follow the rules for that particular case. So you're going to have to assess the degree of the numerator and denominator and kind of go from there. So that's the rest of the notes on this slide. On the next slide, we're gonna go through 3 different examples that if you screenshot from your book, you probably have in your notes right now. But I want to explain each of those, and we'll go through them. So here's the first example I want to look at. Okay, same page, and it's just the bottom of that box in your book. Okay. Now let's look at the actual function for a second. Okay, x squared on top, x plus 1 on the bottom. Can't factor it, can't reduce. This is a loner, this is a group. I can't cancel those out. The degree of the numerator is what? 2. What's the degree of the denominator? Okay, so the degree is greater on top than it is on the bottom. That's the first example, which means there is no vertical asymptote. And now, there's a whole area here in between these two that it doesn't hit, but it's not one particular line. So in this case, because the degree is bigger on top than it is on the bottom, no vertical asymptote. The only asymptote that we have is, horizontal asymptote. I said vertical, I meant horizontal asymptote, sorry. There's only a vertical asymptote, and that is when x equals -1, because, again, opposite sign, but the same way to look at it is if x equaled -1, this whole bottom would be 0, which would make it undefined. So you see a vertical line at x equals -1. Here's the next example, okay? Now in this case, okay, the degree on the top is what? 0. Okay, the degree on the bottom is 2. So the degree on top is less than the degree on the bottom, which means there's one horizontal asymptote, f of x equals 0, y equals 0. Okay? These values, if I factored this out, I'd have x plus 1, x minus 1, which is why x equals -1 and 1. Both of these values make the denominator 0, which means that's where it would be undefined. So therefore I have a vertical asymptote at -1, and I have a vertical asymptote at 1. X equals -1, x equals 1. Okay, that's a lot like the example on your quiz from yesterday. Or 2 days ago, excuse me. Correct. And then, so we have where the degree on top is bigger, we have the degree on top is smaller. Now we need to look at where they're equal. And so we want to see exactly how this works. Again, the vertical asymptote, finding that equation is no different than what we've been doing. What makes the denominator 0? Okay. The horizontal asymptote in this case is f of x equals 2, and here's how we know that. What you essentially do here, okay, since the degree, you take the leading coefficient, so here's the ones that we're matching up. We're matching up 2x and x. The coefficients are 2 and 1. So in reality, I don't even need the x's, they cancel anyway. So when those degrees on top and bottom are the same, all you do is divide the coefficients. 2 divided by 1 is 2, and therefore I get this horizontal asymptote at f of x equals 2. Okay? So that's really the only difference.
Can you do that again?
Sure. So right here, since the degrees are the same, I take the leading coefficient, 2x divided by x. It's actually 2 divided by 1. So my horizontal asymptote is f of x equals 2, because 2 over 1 is 2. So anytime the degrees are the same on the top and the bottom, to find the horizontal asymptote, all you have to do is divide the leading coefficients. Okay? Whether this was, these could both be x squared and it'd be the same thing. They could both be x to the third, it'd be the same thing. 2 divided by 1, still going to give me 2. Okay? You just have to, when the degrees are the same, you divide those leading coefficients. Other questions on that before I move on to an example? So again, you have 3 scenarios that you have to watch out for, and in each scenario, what you do for the horizontal asymptote is a little bit different. Okay? If the degree on top is bigger than the bottom, there's no horizontal asymptote. If the degree on bottom is bigger, then there is a horizontal asymptote at f of x or y equals 0. If the degrees are equal, you divide the leading coefficients to come up with the horizontal asymptote. That's what it is in summary. Okay? Here's an example that we're going to look at. So while you're working on your homework, you're going to want to have those 3 different scenarios from your notes kind of off to the side maybe. You might even copy paste it and put it right at the top of your homework so that you can refer back to it each time. Because those 3 different scenarios about the degree of the numerator versus the degree of the denominator apply only to the horizontal asymptote. Okay? The vertical asymptote is the same. Finding the table of values from your graphing calculator is the same as what we've already done. Graphing your points is the same as what you've already done. Okay? It's just to determine the horizontal asymptotes that you have to worry about the difference. Here's where we're going to start. We're going to start with finding the zeros when possible. And that is about the numerator equal 0. Okay? Finding what makes the numerator equal 0. So what we're really doing is saying you're solving this equation. X to the third equals 0. Because that's the numerator. So how do I solve this equation? Cube root. Undo the cubing. So I cube root sides. Okay? And my little program that I do equations on, for some reason, puts this little like tail on the radical. I don't know why. That's all that is. That's just a funky thing from the calculator or the program that I use. Okay. So what's the cube root of x cubed? X. What's the cube root of 0? 0. So I have a 0 at x equals 0. So it's going to actually cross the grid at 0, 0 at the origin. Okay. So that's one of the things that you're going to want to do when you graph these. Okay. When possible. All right, next thing we want to do is we want to find and draw the asymptotes. The vertical one's easy, right? All I need to do is look at the bottom. What value for x is going to make this equal 0? 1. If x was 0, we'd have a problem. So my vertical asymptote is just x 1. Vertical asymptote is x equals 1. It makes the bottom 0. Or, the way we looked at it before, opposite sign. Okay, and again, the reason is because it makes the bottom 0, which is where there would be a problem. Now, let's talk about horizontal asymptote next. Okay, so for horizontal asymptote, we have to look at the degree of the top compared to the degree of the bottom. And what would we say there?
There's none because the degree on the top is higher than the bottom line.
Okay, that's the key. Hold on, no. The degree of the top is what? 3. The degree of the bottom is what?
1.
Okay, so the degree of the top is bigger, It's greater than the bottom, which means what about the horizontal asymptote?
There is none.
There is no horizontal asymptote, okay? So each time you go through these steps, when you get to horizontal asymptote, what you're doing is comparing the degree of the top to the degree of the bottom. So either you have three scenarios. The horizontal asymptote will not exist when the degree is higher than the bottom. Okay, the degree of the top is higher than the bottom, no horizontal asymptote. When the degree of the bottom is higher than the top, then it's f of x or y equals 0. If they are equal to each other, the degrees are equal to each other, you divide the leading coefficients to come up with your horizontal asymptote. Alright? How many of you already plugged this in your calculator? If you didn't, do that. And then let's look at your table, because the next thing we need is the table of values before we can graph it. Here's what your table should have been. These are the table values I use. Now, obviously, I'm not going to make my graph go up to 43 or 31 or 21, okay? But the reason I wanted to show you that is you have to make some judgments when you create your grid. See, if I went up higher if I went lower actually to -5, obviously this value is going to be bigger than 12, right? And if I'm only working with a 10 by 10 grid, this isn't going to really work. I'm going to need either some points in between here, okay, or I'm going to have to expand my grid a little bit. So this is something we haven't really talked about because I've left it up to you. But there's going to come a point where you're going to need to make a decision in order to make your points fit on your graph. Because if you only have a 10 by 10 grid, for this part of the graph, you're only going to have 1 point, right? I probably need a value in between 1 and 2, or in between 2 and 3, to help me get a better look at what my points are going to be. And what you can do in your on your calculator is in table settings, which is right above the window button. Okay, as it stands right now, your table below, you see a little triangle and then it says table and it says equals 1. Okay, that means change of the table. So if you wanted to make it go by a certain decimal, instead of going by ones, you could just change it to 0.5 or 0.25 or whatever, and it would adjust your X column so you can get more points, which means you will get more Y values. So that's just in table settings, above window, second window, and you can adjust your X values by the delta table, change in table, and make it change instead of by ones, you can make it change by a decimal, you can make it change by fives. Whatever you want to set it at, you can set it. Okay. Ultimately, this is what your graph should have looked like, and I grabbed the one from the book, and my graph goes up to 14 here. Okay, and yeah, it is a funky graph. And so when you've got a cubic and you also have a linear function, this is what it will look like. Okay, so I just wanted to talk about this table a little bit and make sure you're clear on how you can adjust your calculator to give yourself more values, because like I said, in between here, in between 1 and 2, trying to get some values in here to graph would be a little tougher if these are the numbers that you use. Okay, so summary, let's put a bow on this thing. Most of what we're doing is not really new. The biggest thing has to do with horizontal asymptotes. When the degree on top is bigger than the degree on the bottom, no horizontal asymptote. When the degree on top is smaller than the degree on the bottom, the asymptote is y equals 0 or f of x equals 0. If the degree on top is equal to the degree on the bottom, divide the leading coefficients and that will be your horizontal asymptote, y equals whatever that is. Again, there is at most one horizontal asymptote for rational functions. Okay?